sketch the graph of the function f of x equals 6x squared minus x to the fourth by determining the parts a through I. F of x equals 6x squared minus x to the fourth, which is a polynomial. Therefore, for part A, the domain will be all real numbers, or negative infinity to positive infinity. For part B, we want to determine if there is any symmetry. This is done by evaluating f of negative x and comparing it to the original function f of x. F of x is made up of two even powers combined together, and therefore it will have even or y-axis symmetry. F of negative x is 6 times negative x squared minus negative x to the fourth. Negative squared is positive, x squared times 6, which will be 6x squared. A negative to the fourth is positive, x to the fourth, and times the negative will be negative x to the fourth. Comparing this result to the original, it exactly matches it. Therefore, f of negative x equals f of x, which is the condition needed to have y-axis, also known as even symmetry. This means that the graph will be the mirror image of itself over the y-axis, so we will be sure that that is the case. For part C, we want to determine the y-intercept. This is the point where the graph crosses the y-axis, defined by x equals 0. We can find the corresponding y-coordinate by plugging the x-coordinate of 0 back into the original function, so f of 0, which is 6 times 0 squared minus 0 to the fourth. 0 squared is 0 times 6 is 0 minus 0 to the fourth, which is 0. 0 minus 0 equals 0. We have the x-coordinate of 0. We found the corresponding y-coordinate to also be 0. And there's the y-intercept. For part D, we want to determine the x-intercepts. These are the points where the graph crosses the x-axis, defined by y equals 0. So y, which is f of x, is going to be made to be a 0, and we're going to solve for all x's. We will want the function to be fully factored for this. So back up here, let's factor the function. It has a common factor of x squared. Factoring that out will leave behind 6 minus x squared, which is a difference of squares. 6 is not a perfect integer square, but it can be thought of as root 6 squared. Root 6 times root 6 is 6. And therefore, it can factor as a difference of squares into root 6 plus x and root 6 minus x. So y, which is f of x, is a 0, and it can be set equal to the factored version of the function x squared root 6 plus x and root 6 minus x. We can now easily solve for each of the x values. X equals 0, x equals negative root 6, and x equals positive root 6. It has a y-coordinate of 0. These are the corresponding x-coordinates. So we have 0, 0. We have negative root 6, 0. And we have positive root 6, 0 as the three x-intercepts. For part E, we want to determine any vertical asymptotes. F of x is a polynomial with no denominator, so it will have none. For part F, we want to determine any holes. F of x has no denominator, so it will have none. For part G, we want to determine any end behavior, horizontal asymptotes, or slant asymptotes. F of x is a polynomial with no denominator, so it will not have horizontal asymptotes or slant asymptotes. But by being a polynomial, it will have end behavior of positive infinity or negative infinity. We can find the left end behavior by taking the limit as x approaches negative infinity of the function 6x squared minus x to the fourth. Only the highest power term matters here. Negative infinity to the fourth is positive infinity, times the negative is negative infinity. We can determine the right end behavior by taking the limit as x approaches positive infinity of the function, 6x squared minus x to the fourth. Again, only the highest power term matters here. Positive infinity to the fourth is positive infinity times the negative will be negative infinity. The highest power term is even, and therefore the left end and right end behaviors will have the same sign of infinity. They are both negative infinity here. For part H, we will determine the intervals of trend, relative maxima, relative minima, plateaus, and cliffs. This all involves the first derivative, f prime of x, which we can take from f of x, and it will be 12x minus 4x cubed. We want to fully factor the first derivative. There's a common factor of 4 as well as an x. Factoring those out will leave behind a 3 minus x squared, which once again is a difference of squares if we think of 3 as root 3 squared. So it can further factor into root 3 plus x and root 3 minus x. We can now set the numerator equal to 0 and the denominator, if there is one, also equal to 0. Solve for all x's. Since it's factored, we can see that x equals 0, x equals negative root 3, and x equals positive root 3. We will now check to see which of these are in the domain. The domain is all real numbers. Each of these are a real number. The square root of 3 is a real number. It's a decimal, but it is a real number. Each of them are in the domain. Each of them are a critical number. We can now draw a domain line, a line representing the domain. It has no left end because it begins at negative infinity. It has no right end because it ends at positive infinity. We can put each of the critical numbers on here in order. Negative root 3 will come first, then the 0, then the positive root 3, which splits the domain interval up into 4 separate intervals. We can pick a test value in each of these intervals. The square root of 3 is somewhere between the square root of 1, which is a 1, and the square root of 4, which is a 2. So it's somewhere between a 1 and a 2. So the first interval, negative infinity to negative square root of 3, will definitely contain negative 10. The next interval, negative square root of 3 to 0, square root of 3 is bigger than 1, so negative square root of 3 will be more negative than negative 1, so negative 1 will be in there. The next interval, 0 to the positive square root of 3, positive 1 will be in there, and then positive square root of 3 to positive infinity, 10 will be in there. We can test the trend by plugging the test values into the first derivative. We only care whether it is positive or negative. Therefore, we'll plug into the fully factored version. Plugging the first test value of negative 10 in, 4 times negative 10 is a negative. Square root of 3 plus a negative 10 is a negative. Negative times negative is a positive. Square root of 3 minus a negative 10 is square root of 3 plus 10, which is a positive. Positive times positive is positive. We have a positive first derivative, which corresponds to an increasing trend. Plugging in the next test value of negative 1 into the fully factored version, 4 times negative 1 is a negative. Square root of 3 plus a negative 1 is a positive. Negative times positive is negative. Square root of 3 minus a negative 1 is the square root of 3 plus 1, which is a positive. We have a negative times a positive, which is a negative. A negative first derivative corresponds to a decreasing trend. Plugging in the test value of x equals positive 1 into the fully factored version, 4 times positive 1 is positive. Square root of 3 plus 1 is positive. Positive times positive is positive. Square root of 3 minus 1 is also positive. Positive times positive is positive. We have a positive first derivative. This corresponds to an increasing trend. Plugging in the test value of x equals positive 10, 4 times positive 10 is positive, times the square root of 3 plus 10, which is positive. Positive times positive is positive. Square root of 3 minus 10 is a negative. Positive times negative is a negative. We have a negative first derivative, which corresponds to a decreasing trend. Right at the critical number of x equals the negative square root of 3, we have the trend changing from increasing to decreasing, so x equals negative square root of 3 will be a relative maximum. It has an x coordinate of negative square root of 3, and a corresponding y-coordinate, which can be found by plugging the x-coordinate back into the original function. So y equals f of negative square root of 3, which is 6 times negative square root of 3 squared minus negative square root of 3 to the 4th. So this will be 6 times, negative squared is positive, square root of 3 squared is a 3, minus, a negative to the 4th is positive, square root of 3 to the 4th is square root of 3 times square root of 3, which is a 3, times another square root of 3 times another square root of 3, which is another 3. 3 times 3 is a 9. 6 times 3 is 18, minus 9 equals 9. We have a corresponding y-coordinate of 9. Right at the critical number x equals 0, we have a trend change from decreasing to increasing. So x equals 0 will be a relative minimum. It has an x-coordinate of 0 and a corresponding y-coordinate, which can be found by plugging the x-coordinate back into the original function. Y equals f of 0, which is 6 times 0 squared minus 0 to the 4th. 0 squared is 0 times 6 is 0 minus 0 to the 4th, which is also 0. 0 minus 0 is 0, so we have a corresponding y-coordinate of 0. Right at the critical number of x equals positive square root of 3, we have a trend change from increasing to decreasing. That makes x equals the positive square root of 3 be a relative maximum. It has an x-coordinate of positive square root of 3, and it has a corresponding y-coordinate, which can be found by plugging the x-coordinate into the original function, so f of the square root of 3, which is 6 times square root of 3 squared minus square root of 3 to the 4th. So it'll be 6 times the square root of 3 squared is a 3 minus the square root of 3 to the 4th. Square root of 3 times square root of 3 is 3, times another square root of 3 times another square root of 3 is another 3, and again it's a 9. 6 times 3 is an 18, minus 9 is 9, so we have a corresponding y-coordinate of 9. For part I, we want to determine the intervals of concavity as well as any inflection points. This will require the second derivative, f double prime of x, taken from the first derivative, will be 12 minus 12x squared. We want to fully factor the second derivative. There's a common factor of 12. Factoring that out will be behind 1 minus x squared, which is a difference of squares and can further factor into 1 plus x and 1 minus x. Setting this equal to 0, and solving for all x's gives x equals negative 1 and x equals positive 1. We'll check to see which of these are in the domain. The domain is all real numbers. These are both real numbers. They are both in the domain. They are both candidate numbers. We can now draw a domain line, a line representing the domain. It has no left end because it begins at negative infinity, no right end, it ends at positive infinity. We can put the candidate numbers on here in order. We have a negative 1, we have a positive 1, which splits the domain interval into 3 separate intervals. We can pick a test value in each of the intervals. The first interval, negative infinity to negative 1, contains negative 10. The next interval, negative 1 to positive 1, contains 0. The next interval, positive 1 to positive infinity, contains positive 10. We can test the concavity by plugging these test values into the second derivative. We only care whether it is positive or negative, so we will plug into the fully factored version, which is this one here. Starting with the test value of negative 10, 1 plus a negative 10 is negative. 1 minus a negative 10, which is 1 plus 10, is a positive. Negative times positive is negative times the 12 will still be negative. We have a negative second derivative, which corresponds to concave down. Plugging in the test value of 0 into the fully factored version. 1 plus 0 is positive. 1 minus 0 is positive. Positive times positive is positive. Times the 12 will still be positive. We have a positive second derivative, which corresponds to concave up. Plugging the test value of 10 in, to the fully factored version. 1 plus 10 is positive, 1 minus 10 is negative, positive times negative is negative, times the 12 will still be negative. We have a negative second derivative. This corresponds to concave down. Right at the candidate number of x equals -1, we have a concavity change from concave down to concave up. So x equals -1 will be an inflection point. It has an x-coordinate of -1. It has a y-coordinate that can be found by plugging the x-coordinate back into the original function. So y equals f of -1, which is 6 times -1 squared minus -1 to the 4th. -1 squared is +1. -1 to the 4th is +1, then with a minus. 6 times 1 is 6, minus 1 is 5. We have a corresponding y-coordinate of 5. Right at the candidate number of x equals +1, we have the concavity changing from concave up to concave down. That makes x equals +1 also be an inflection point. It has an x-coordinate of +1, and a corresponding y-coordinate can be found by plugging the x-coordinate back into the original function. So f of 1, which is 6 times 1 squared minus 1 to the 4th. 1 squared is 1, minus 1 to the 4th is also 1. 6 times 1 is 6, minus 1 equals 5. And it will also have a corresponding y-coordinate of 5. We can now draw the graph. We have a vertical axis and a horizontal axis. The domain is all real numbers, so it will extend across all x values and along the entire x-axis. We have y-axis even symmetry. That means that the graph will be a mirror image of itself over the y-axis. So whatever we see here, we will see over here flipped around. We'll be sure that's the case. We have a y-intercept that is the origin. So we'll put that on there and we can label it. It is 0, 0. We have 3 x-intercepts. One of them is once again the origin, which is no surprise, because if the origin is the y-intercept, it will also be one of the x-intercepts because it's crossing both axes when it passes through the origin. But we also have negative square root of 6, comma 0, and positive square root of 6, comma 0. Square root of 6 sits somewhere between the square root of 4, which is a 2, and the square root of 9, which is a 3, somewhere between 2 and 3. We have a negative square root of 6, which will be over here somewhere, comma 0. And we have a positive square root of 6, which will be the same distance from the origin, but over on the positive side. And we can label each of these as the other x-intercepts. We have no vertical asymptotes, no holes. We have left end behavior of negative infinity. That means over at the left end it's going to travel down to negative infinity. It'll end up down here. And we have right end behavior also of negative infinity, so at the right end it will also travel down to negative infinity. So it'll end up down on both ends. We'll be sure that that is the case. We have a relative maximum occurring at negative square root of 3, comma 9. Now square root of 3 is not as big as square root of 6, and negative square root of 3 will not be as negative as negative square root of 6. And that has a y-coordinate of 9, so we'll end up somewhere up here. We can label this as negative square root of 3, comma 9. And this is going to be a relative maximum, so we'll give it a relative maximum kind of shape. We have a relative minimum occurring at 0, 0, the origin, so we can give this a relative minimum kind of shape, like so. And we have another relative maximum at the positive square root of 3, 9. So it'll be at the same height and the same distance away, so somewhere approximately about right here. We can label that as positive square root of 3, 9, and give it a relative maximum kind of shape. We have an inflection point at -1, 5. That'll be somewhere about right here. We can label it as -1, 5. And that's going to be where the concavity changes from being concave down on the left. So on the left it's going to be curving down the entire time, kind of curved down like so. And then beyond this inflection point, it's going to become concave up and start curving upward instead. So we can connect that together. We have another inflection point occurring at +1, 5. So that'll sit somewhere about right here. Again, we can label this one. This is +1, 5. And on the left side of it, it's still concave up, so it's curving upward. But right there, it's going to change and start curving downward. And then it's going to stay curving downward for the rest of the time, like so. Notice that it does have the domain of all real numbers. It extends over all of the x values. And it is showing the y-axis even symmetry. It is a mirror image of itself over the y-axis as it should be. And it has the left-end and right-end behaviors of negative infinity, as it should. So all properties are being held. And therefore, this is the graph of f of x.